So welcome, everybody. Welcome, everybody online. Glad you could join us. I do not have slides for a report today, but I have a handful of exhibits, upcoming events that I'm going to go through for you, especially because we don't have an outreach report. So the first thing I'm going to talk about is the York County Star Party. It's funny, I just checked the website for it, and you got to love Phil DeRosa. He puts his heart and soul into the York County Star Party, but he doesn't tell you where it is. And I'll tell you, in fact, then I went to his website and he goes, it's 10 miles south of Lancaster, less than 50 miles from Baltimore. While not the darkest, it's dark. Less than 90 miles from DC or Philly. It's in a state park right on the Susquehanna. And I went there, I was there last year. He's doing two of them. The first one is going to be June 22nd to June 26th. You have to register. It's a great location. There's a baseball field, wide open baseball field. People have campers or tents. There's plumbing. There's no electrical, but there is a pavilion that he reserves, and you can recharge batteries at the pavilion. The second one is going to be September 21 to 26, September 21 to 25. It's rain or shine, regardless of the weather. And last year we had a couple really decent nights of observing out there. It was a lot of fun. The next thing I want to report. Thank you for catching me on that. It's www.yorkcountystarparty.org. I'll repeat that. www.yorkcountystarparty.org. And there's a groups IO, and Phil's very helpful. If you have any questions, just email him, and he'll talk it out. Okay. Yeah, Bill. I would call them comparable to Blue Mountain, very close to Blue Mountain. I'm trying to remember, Blue Mountain, it's a little tougher to see up north on Blue Mountain, not so much here. The horizons are a little bit lower. Also, because the altitude isn't as high as Blue Mountain, it doesn't get quite as chilly, although you may get a little bit of humidity. But I had a good, I can't remember if it was 2 or 3 nights, but good observing last year. I had a good time. The second thing I want to mention is we got an email from Anne. Oh, I'm going to have to put my glasses on for this. For Anne Marie Schmeidekamp, who is a professor at Penn State Abington. She wanted to forward some information to DVAA to interpret the James Webb Telescope's first release images, which will be released in mid-July. They are going to have an interpretive program on July 24th from 2 o'clock to 4 o'clock p.m. at Penn State Abington in Abington. They're planning on a presentation to interpret the images which have not yet been released. And we hope to have related demonstrations suitable for school-age children or adults, or school-age adults, I suppose. It's a community event. Everybody's welcome. I think Janet's going to put this on the website. So this event will. This is July 24th, midday, 2 to 4 p.m. What else? Chesmont is going up to Cherry Springs, I believe, late July. The problem, of course, is once again, the Woodsman's Festival starts in the middle of the new moon week. I don't understand how they do this, but everybody has to be off the field Sunday, July 31st. So you can get up there like the last week, but you got to be out of there by July 31st, even though viewing will still be good from after that. We're going to have a July meeting, but we will be back at Fort Washington State Park on August 19th for a combination Star Party and meeting. Starfest, Chesmont's Starfest at at Hopewell Furnace is August 20th. That's a great event. That's just, you don't even have to take a scope because the members set up scopes. There's talks, there's door prizes. I love that event. I take my scope, but I love that event. That's a great event. Let's see, that's Starfest. And I'm going to Cherry Springs August 26th. If anybody wants to, I'll go up there for about 5 or 6 days. I try and get away every summer and put it on my calendar. No court dates, no depositions, no nothing. I'm going to Cherry Springs, weather permitting. And that's all I have on events. If you have any questions, you can go to the website, dvaa.org. All events are up there, not just the ones I chose to report today. And that is all I have for now. Brian, anything?
We have one new member, Brian Crozier.
Brian, are you here? Okay. Shy, but not here, or not here. Okay, great. That's good. It's always good to have new members. Glad to see it. Yes.
Regarding the Lisbon's festival, I think they said in the future they're going to move across the street.
Well, that'd be good. That'd be good. Then it won't be too much of a traffic jam. But yeah, that'd be great if they move it across the street. They were supposed to do some improvements at
Next year.
yeah, well, they were supposed to do some improvements and then the pandemic hit, and that was the end of that. But they were going to improve the astronomy field.
Yeah, they're going to improve it and they're going to be doing it in July, August, September. So
Yeah. I'd also mention they're out of Galaxy passes. So you got to pay the $15 a night fee. I called and said they were out. Yeah, Brian.
one other thing, if you're a member, you're not the box, name on the list, I'll make sure you get it back.
Okay, and I will repeat that for our TV crowd. If you don't have a name tag, come here and put your name on the list so Brian can make you a name tag, okay? All right. Lou is not here. There was a photography session Wednesday night with a Greek planetary astronaut talking about, somebody correct me if I get this wrong, atmospheric, something that corrects for the atmosphere. And he was viewing Saturn at about 30 degrees, and it was amazing what he was able to do with a device that, as he explained, it used to cost thousands of dollars, but now if you get the ZWO product, it's $125, because I was Googling it while I was watching this program, and it was amazing what you could do with images and sort of completely remove the effect of the atmosphere when you're taking planetary photography. It was a great program, very, very well attended, and thanks to Lou and to Agapios, who did it live from Cyprus. Yes, Brian. Oh, it's on YouTube also. Yeah, if you missed it, watch it. I will say this. For somebody like me who likes to when I take a picture, it's with my cell phone through the eyepiece. It was extremely technical. Like, I don't stack. I don't run software. But if you do, and if you have taken or even a passing interest in astrophotography, this was a great program. I would call it pretty damn close to introductory level. Over my head, but that's not saying very much. But it was a really good program. Roy's not here, so Andrew, you're up with the observing report.
All right, great. Thanks, Jeremy. Thanks, Harold. So good to see everybody again. My name is Andrew, if any of you forgot. I'm the observing chair, and this is the DVAA observing report for June 2022. And I'm going to see if this works. It does not, so I'm going to click this button. All right.
I got to bring the mouse over to the right.
Click that. There we go. All right. So, and then this month we're going to be talking about the constellation Lyra. Some people say Lyra. I like to say Lyre. It's a little liar. And you can see it pretty much right there. It's a smaller constellation, but it's a very easily distinguishable constellation because of that really nice triangle up at the top there. And then we have the parallelogram asters and down in the bottom. So we're going to be going through that and then pointing out some interesting objects in Lyra. But first, we're going to give a little bit of an overview. And again, it's a pretty small constellation, but it's very easy to pick out in the night sky. It is kind of a Milky Way constellation, if you will, but it's a little bit right off of the Milky Way. And as I was going through the objects, it actually has a lot of very well-known stars in it, which I always find interesting. A lot of us don't directly observe stars, but stars are all up there, and there are some pretty interesting ones just by themselves. So we'll take a look at those. And then there's also a very well-known planetary nebula, and there's actually a fair number of galaxies, also kind of not indicative of a Milky Way constellation. So we'll take a look at those. And then again, here we have the star chart. So the alpha star Vega, we'll talk about that in a while. We all know Epsilon, Lyrae, the double double. And then there's also some more interesting stars that we'll talk to later. So let's start with Vega. So Vega by itself, it's a pretty star. It's very bright. It's usually right at nadir from where we are in the Northern Hemisphere. It's a nice blue-white star. But what's interesting about it is that Vega is the quote unquote 0 point for the magnitude system, for the visual magnitude system. Now, it's not actually magnitude 0. We have since changed it to be just very slightly above 0, but semantics, for all practical purposes, it's 0. And then again, this is the star that all other brightnesses are based off of. So as far as observing it, you can do it in any which way. You can do it naked eye with any kind of optical aid. It can be done in any brightness of sky, and it's just a really nice star to point out to people when you're outside. All right, next we have the double double, and this is going to tie a little bit into Bart's talk on double stars if you were here last month. So the double double Epsilon Lyrae is a double star unto itself, but then each of those individual components, the A and B, are then double stars themselves. And what's interesting is that the two double stars are also gravitationally bound here, so they are binary stars as well. And it's just a very popular way to test out your observing skills and your optical system. If you can split the double double, as they say, then you have a pretty good telescope. You have a pretty good optical setup there. And it also means that you're using pretty good skies and that you're a pretty good observer. So yes.
What kind of aperture do you need to do that?
The aperture, I mean, that's going to depend. It's escaping me right now. What's it? Yeah.
Like ETX 90, it's no problem.
Yeah. If you want to calculate a theoretical limit, there is that chart that Bart showed where it was like the aperture and resolving power, if you will. It escapes me what formula that is, but Bart did talk about like the theoretical aperture.
I know that formula, for that kind of star system,
Mhm.
how big a glass do you need?
Yeah.
You can do it with binoculars.
Pretty much any will do it.
Mhm.
It's like a 2 to 3 arc-second separation, so anything over like 50 or 60 millimeters should be able to do it.
Oh, okay.
Yeah, I've definitely seen it in binoculars. Now they were slightly larger binoculars, but it is definitely a fun challenge to try and pick it out. So no, good question. Thank you. So now along those same lines, there is actually a double, if you will, in Lyra. So there are two stars, Struve 2470 and 2474. Now, by they themselves don't make a double star. Each of them are a double star, if that makes any sense. So up here you have one star, 2474, and up here you have another star, 2470. And what makes this interesting is that, the double Epsilon Lyra is interesting, but visually speaking, the colors of the stars, they're kind of all white. So I really like observing double stars because I like to see like the nice color contrasts and all. These two Struve stars are nice because the one pair is a kind of yellowish pair, and then the other pair is a kind of yellow-blue pair, so indicative of Alberia. So it's kind of off the beaten path. It's a star star system that not a lot of people realize and take a look. So it's definitely something to look at if you're looking for something in the Lyra area. All right, and now we're going to talk about another star, Shellac. think I'm saying that correctly. It's actually Beta Lyra. Okay, so it's the second brightest star in the Lyra constellation. And what's interesting about this one is that it's actually a prototype star for a variable star type. So all of the variable stars, there was originally one star that was found to have those characteristics of all of the variable star types. And then we call that the prototype star. So Shellac is the first prototype star of the Lyrid eclipsing binary stars. So what that means is that when you observe this star, it is actually a multiple star system, but we cannot separate the two visually. But we know there are two stars because the brightness changes. As one star rotates in front of the other, then it will dim slightly. And then as they rotate back into the same field of view as us, then it will get brighter. So just the specifics, it will go from magnitude 3.4 to 4.4 in a 13-day period, which is actually pretty doable. You can go out there and observe this directly. It is a great way to get into variable star observing because what you do is you can look at shellac, you can compare the brightness of that to the stars around it, which are stable stars. And then you can figure out the period and of that. You can even figure out the rotation period of the two stars. So it's pretty interesting. And again, right in the constellation Lyra. Yes. What's that? I can't hear you. I'm sorry, what? Okay.
Fraction.
Okay. All right. So the Ring Nebula M57. So this is again one of the really popular objects in Lyra. And it's pretty beautiful. Again, you can see it. You're going to need dark-ish skies to see it. I don't think you're going to see it downtown Philly, but we definitely see it over in Valley Forge, which is about Bordeaux 5 or so. So it's very easy to see with the smaller aperture. You'll kind of see the ring. You might need inverted vision to see the middle to the actual donut shape of the nebula. And as you increase aperture, that's going to be more apparent. And another good challenge here, we're talking about challenges, so is to try and pick out that white dwarf in the middle. So you can see the star that actually formed the planetary nebula here. And I've definitely seen it at Blue Mountain, although it does take a lot of patience. It takes very good seeing and transparency, and you need to know what you're looking for too. But it's pretty fun to try and pick up. All right, now the other Messier object in Lyra is M56. So it's about 31,000 light years away, and it is a globular cluster. Now I put down here that it's class 10, meaning that it's actually pretty dispersed for a globular cluster. And yeah, it's pretty nice. You can pretty much view this with any telescope size, although of course, the larger the aperture, the more individual stars you'll be able to pick out in the globular cluster. Then there's actually an open cluster in Lyra, NGC 6791. I thought that this was pretty interesting because it's a good example of how it's kind of, as you get more dispersed globular clusters and more concentrated open clusters, you kind of wonder, well, where is the line drawn? So if you look at this, it kind of looks like a very dispersed globular cluster. And if we look at the Trumpler class, the TR type, I2R, the I means that it's actually pretty concentrated. The 2 means that it's even brightness. And the R means that it's very rich in stars. So it does actually look like a globular cluster, and probably a few thousands, millions of years from now, it might actually be classified as a globular cluster. But it is pretty nice to look at. You are going to need a modest telescope size to see this one, and pretty dark skies if you want to pick out individual stars. All right, and last I wanted to talk about the interesting galaxies. So I wasn't really expecting to find galaxies in Lyra because, again, it is considered a Milky Way constellation, and we don't usually see a lot of galaxies in the Milky Way. But there are actually a few. So here's 2 for an example. I believe it's NGC 6702 and 6703. And you can easily get these in the same field of view, and then with a bunch of other galaxies, especially if you're imaging in that area. And you probably need about an 8-inch telescope minimum. 12 plus would probably be optimal. So Brian. I don't know that. Yeah, so that is a I will say that that is a very cropped image. So the field of view is a lot larger than that. So the two are pretty small or pretty close together. So you can easily see them within the same field of view. And because we're observing galaxies, you'll probably want not the highest magnification, probably a modest magnification. So you'll get a pretty wide field of view when doing them. But that's a good question. There are other, if you do image in this area, there are other galaxies that you might not be able to see with the eye that are on the UGC catalog, which are much fainter. So, and then I included down here, it's a little hard to see, but all of these red circles here are galaxies. And it just goes to show how many there are in the area. They're all NGC objects. And they're all relatively easy to find because, again, we have that nice bright star Vega as an easy starting point for star hopping. So, and I believe that's my last slide. So thank you, everyone.
Jeremy, why don't you introduce our speaker?
Yeah, our speaker this month is a very illustrious person. This brings me the greatest pleasure to introduce the person who is the most important individual in influencing my life, and that would be me. All right, so a little update on some upcoming talks. In July, we're going to have a member night. So I'm actually looking for presentations for that. So if anyone has a presentation you want to give, send me an email. I'm hoping to get the lineup together by the end of the month. That way we can get that out in the newsletter. So July will be a member night. That'll be July 15th. Then August 19th, we're going to have an outdoor in-person meeting, and that'll be at Fort Washington State Park. So that's similar to the one that we did last year. So we'll be doing that again. It'll be kind of an astronomy fair format with different topics, and then maybe some observing at the end of that. In September, we're going to have Professor Dave Goldberg from Drexel University. And then in November, we're going to have Rick Schwartz, who's a DVAA member, and he's doing some exoplanet research. So he's going to talk about that. We do have a few other speakers, but I haven't firmed up the schedules with them yet. So tonight's presentation will be me. My name is Jeremy Carlo. I'm a professor at Villanova University. Let me bring up the little presentation here. Share screens. Go. So let's see if this works. There we go. All right, so tonight's presentation is called Fermi Questions, Thinking Like a Physicist. Before I get into it, Andrew, I'm glad you mentioned the other double-double with Struve 24, 70, and 74. That's one of my favorite objects. It's kind of a secret thing that most people don't know about.
Oh,
So definitely check that out.
Sorry.
What's that? No, we could leave them on. Yeah, I don't have any pretty pictures here. It's all going to be thinking. Yeah, it's a great object. It's a lot easier to split than the regular double-double because the elements are further separated and nice colors too. It is a little dimmer, so that's the hard part. All right, so wrong way. So what are Fermi questions? Well, the name Fermi comes from Enrico Fermi, who is one of the most famous physicists of the mid-20th century. So he led the initial nuclear fission experiments at the University of Chicago. They had the first controlled nuclear reactions. Actually happened underneath the bleachers over there. Bill, if anyone has any questions on YouTube, just shout them out to me. And if anyone else has any questions, shout them out to make sure people can hear, because we're just using the little microphone here. So Enrico Fermi was very famous for being a really smart guy. And, in comparison to other physicists, he was a really, really smart guy. This is the type of guy he'd pick up the journal Physical Review, basically read it cover to cover and sort of understand everything, which is just an amazing feat. I mean, I pick up the Physical Review, I read like 2 or 3 articles that are in my field that are great, and then the rest of them just goes over my head. So Fermi is one of these brilliant guys, and he had this real knack of being able to just quickly estimate things right off the cuff. Someone would come in with some idea. Hey, do you think we can do this? And he'd take out literally an envelope, like an old envelope from some junk mail, sit there, do some calculations, go, no, that's not going to work. That's off by a factor of 100. Or, oh, here's something that'll work, but maybe do it this way instead. And that's even better. So he was really, really brilliant and well known for these sorts of things. And he would pose these questions to people. It became known as Fermi questions to sort of estimate things that are really complicated, kind of doing them off the cuff using a back of the envelope or a piece of scrap paper and a pencil. And sometimes this is very worthwhile because sometimes the detailed calculation is really complicated. Yeah,
Was he
right.
also noted for using a slide rule?
That too. So yeah, he used a slide rule. So anyone brought their slide rule tonight?
Like the moment.
Oh, you guys are going to be lost. Yeah. So sometimes the detailed calculation is really difficult. It might involve a lot of computational time. You could sit there spending a month working out all the calculations, doing integrals and figuring out shapes and things like that. But you could just do something really, really simple, assume the spherical cow, right? Makes things a lot simpler. And you could do a calculation in 5 minutes. And sometimes that's good because it tells you, is something even feasible? So I come up with an idea, say electricity is cheaper at night than it is during the day. So what I'll do is I'll use electricity during the night and I'll figure out a way to store energy, and then I'll use that during the day. So maybe a way to do that, if I have a swimming pool, I'll pump the water from the swimming pool up to a higher pool, right? So I give it gravitational energy. And then during the day, I let the water flow downhill and get the electrical energy out of that, by spinning a windmill or something like that. Is that even feasible? Is it even possible to do that? You could quickly do that, right? Use your MGH to figure out the gravitational potential energy. See how much there is. Is it enough that you can run a house off of it? Is it even feasible? And if it is, well, okay, then we'll look at the details. If it's not, if it's a factor of 100 too small, then don't even bother. So that's essentially the goal here. We want to break up problems into more manageable parts, or maybe estimate something that is a little too complicated to do on its own. So the classic Fermi question was, how many piano tuners are there in the city of Chicago? This is something that's really not that accessible. So I'll give a variation. How many dentists are there in Pennsylvania? Now, we're lucky we have an actual dentist here tonight. So you can, any other dentists here tonight? One. All right. So you can fact check me on this.
We did an order of
All right. Tell me whether this is fake news. All right. So here's how I approached it. I said, population of Pennsylvania, 10 million. How did I know that? Well, how many congressional districts does Pennsylvania have? Oh, federal congressional. What is it? 16 or 17, and each of those are like 500,000 people or a little more. So I'd multiply that out. Or if I was at a loss, I'd say, what's the US population? 300 million, divide by 50. That's 6 million in an average state. Pennsylvania is bigger than average, so we'll round it up a little. So 10 million. So let's say the average person goes to the dentist twice per year. So that's 20 million dental visits per year. How many patients does a dentist see in a year? Now, Len, here's where you can fact check me. I took a guess. I said 10 patients per day, 250 days per year. The dentist sees 2,500 patients per year. So I divide the two, 20 million visits divided by 2,500 patients per dentist. That's 8,000 dentists, or about one dentist per 1,200 people. So if you were like building a city in the middle of nowhere, if I had 1,200 people, I'd probably want to have one dentist. And that's probably about the right number. So I found the website. I don't know if this is authoritative information or not. They summed them up, and what they came up with is 6,800 total dentists. Maybe there's some other sources that are a little bit different, but this is a question that has an actual answer, right? So, we can call up the ADA and ask, how many people do you have registered in the state of Pennsylvania? And I'm sure there's an answer, right? So it's something that we can estimate like that. And actually, that's not bad. 6,800 versus 8,000 we kind of just came up with. So again, the ideas are these sort of back of the envelope estimates, these spherical cow approximations, and some important ideas here. You want to identify the most important factors and try to ignore the less important ones. So I grade lab reports all the time, and people turn in these papers with like 30% experimental error and 50% experimental error. Sources of error. Rounding by the calculator, because it only counts like 8 digits and then it rounds off after that. That's not giving you 30%. That's not the most important factor. Look at the apparatus. Here's your, crapola experimental apparatus right here. It's shaking around while you're trying to make measurements. That's where your 30% is coming from. Right. So being aware of what the most important factors are and sort of ignore the smaller ones, at least for now. Those are going to be important later on. There are a few caveats to that. Classic example, if you've done any programming, any sort of numerical modeling, let's say I've got two numbers that are about 1 million, right? And I take one number and I subtract the other one from it. And the difference is 17. How confident are you in that number? You got like 1 million, big number, and then like another number that looks about the same, and you subtract them at 17. What if one of those numbers was off by like 1/100%? That's way more than 17. So those are cases where really small things do matter. So that's another thing you have to have in the back of your mind, that sometimes small things do matter, right? It's the butterfly effect. But again, for the purpose of this, we want to find the most important factors, make these approximations, dare to be imprecise, right? Try not to get too bogged down in the details, especially the ones that don't really matter. You can also make estimates with upper and lower bounds, right? Like it's probably between A and B, and you can kind of work both ways on that. And I'll come back to say a little more about that. All right, so here's one. What is the mass of Mount Everest? So there's the detail-oriented way to do this, which means you probably take the picture and do some detailed analysis of what the shape is, and you get some satellite mapping, and you figure out what the composition of Mount Everest is, and do all this stuff. Here's what I'm going to do. I just gave a little information here. Height is 29,000 feet, 5.5 miles, or 8,500 meters if you insist on metric. So here's what I said. The volume is 8 kilometers by 8 kilometers by 8 kilometers. Let's make it a cube. About 500 kilometers cubed. I'm going to round that down because we know that Mount Everest is not a cube. It's technically a cone is 1/3 base times height. So 500 becomes 200. You'll notice that sometimes I'll use numbers for convenience because like 2 times 5 is 10. So I don't have to worry too much. So 200 cubic kilometers, which I convert to cubic meters. So I have to multiply by 1,000 3 times. I'm going to talk a little bit about scaling in the next couple of slides. That this is an easy way to mess yourself up. So that's the volume of Mount Everest. Density of rock. This is another one of the things that people don't have a good handle on. So suppose that I took, if this table, this is about 1 cubic meter. Let's say this table were a container and I filled it with water. What would be the weight of the water inside here?
1 ton per cubic meter, so about a ton.
About a ton. That's a lot. That's a ton of water, right? Most people go, oh, like 100 pounds or 200 pounds. No, it's 2,000 pounds. It's a ton, 1,000 kilograms. So think about the next time you're laying in a bathtub. Think about how much weight the floor is holding up and how amazing it is that you don't end up in the basement. Water's heavy. Cubic foot is 62 pounds, right? A gallon is about 8 pounds. Right? We have a kind of good idea of what that is, right? We know what a gallon of milk weighs, right? It's not too bad, but you feel it. A cubic foot is 62 pounds, a cubic meter, 2,000 pounds, a ton. So it's a lot. Rock is a little denser than water. So I said, well, we'll take that and we'll triple it. So instead of 1,000 kilograms, we'll make it 3,000. Probably about right. 2,000, 3,000. If it was iron, that would be 8,000 because the density of iron is 8. Lead would be 12. Gold would be 20. If you find Mount Everest made out of gold, let me know. So we guess that. Now I take the volume, multiply by the density. I get 6 times 10 to the 14 kilograms, 600 trillion kilograms, and the kilogram's a little over 2 pounds, so it's a little bit over 10 to the 15 pounds. So there is no actual answer to this question. So I'll just go to the internets and see what they have to say. And I just randomly picked some answers in forums. One person said 810 trillion, which is pretty close. Another one said 357 trillion pounds. That's like a factor of 3 or 4 less. Another one said, this is really precise, 9.96 times 10 to the 15 pounds, which is about 10 times higher. So they're all over the place, but you notice they're sort of in the ballpark, right? No one's saying 10 to the 6, no one's saying 10 to the 25, right? They're all like that 10 to the 15, sort of that neighborhood. So yeah, we are sort of agreeing. Pretty interesting. Just to sort of back of the envelope, very simple calculation. We actually get something that's within a factor of a couple of just other answers that I found on the internet. Now, of course, what's the bottom of Mount Everest? We don't really know, right? The foothills of the Himalayas are like 8,000 feet or something like that. So what's the tallest mountain on Earth? measured from base to summit. Mauna Kea, because it starts 15,000 feet below sea level and ends about 13,000 feet above. So it's like 28, 29,000. So it's actually a little bit taller than Everest, because Everest starts at like 10,000, right? That's the lowest you can get, right? The lowest point in the Himalayas is twice as high as the highest point in Pennsylvania. Kind of an interesting idea there. Okay, let's do some astronomy. Suppose that there are 100, or we'll make it any number n, extraterrestrial civilizations in the galaxy right now. On average, how far do you think the nearest one would be? And I'll give you a little information here. Diameter of a galaxy is about 100,000 light years. That's the Andromeda galaxy, but ours looks very similar. How would I approach a problem like this? There's 100 civilizations. How far do you think the nearest one is?
You got the area of the galaxy
Mhm.
and divide that by the number of civilizations.
There's a little scaling that you'll have to do there as well. Yeah, so here's how I did it. If there's 100 civilizations, I picked a square number to make it easy. Assume that they're on a 10 by 10 grid like that. So space them out evenly. So if there's a 10 by 10 grid spaced out over 100,000 light years, that means the average distance between them is 10,000 light years, which means the closest one is 10,000 light years, give or take a little bit. If it was n in general, then the grid would be square root of n by square root of n. And now if you're objecting that n might not be a square number, now you're overthinking. All right, then we're getting a little too far. So square root of n by square root of n. So the average distance would be 1,000 over square root of n. So corollary, suppose that we picked up a radio transmission from a civilization 1,000 light years away. What does that imply about the number of civilizations in the galaxy? Well, take 100,000, divide by the square root of n, and that is equal to 1,000, which means that square root of n is 100, and n is equal to 10,000. So if we got a signal, if SETI came back and said, we've got a signal 1,000 light years away, somebody transmitting a signal, that would imply there's 10,000 other civilizations in the galaxy. If it was 100 light years away, that would imply there's 1,000,000 civilizations in the galaxy. So if SETI were to succeed, it means the universe is just absolutely teeming with life. And I didn't even get into time here, because remember, that civilization might have lived 1,000,000 years ago, or maybe it's 1,000,000 years from now, right? Right now is not really a special time, right? For us it is, but for other planets, it's just, another billion years that goes by.
But Jeremy, you're assuming that the civilizations are all equal.
Yeah, so some of them might be closer, some of them might be further, but this is an average. Right? I guess I could go back here and point out. Yeah, these guys are really, really 9.96, right? Not 9.97, it's 9.96. That's misplaced precision, right? These are numbers that we're pulling out of our butts here, right? And they're claiming like 3 significant figures. It's not at all.
Difference between precision and accuracy.
Yeah. Okay, so a little observation here. We suck with really, really big numbers. So I gave you 2 numbers here. It's just a 1 followed by a bunch of zeros and a 1 followed by a bunch of zeros, right? Most of us look at that and our eyes kind of glaze over. So to prevent you from having to count, the first one has 15 zeros. The second one has 16 zeros. What's the difference between those 2 numbers?
99%.
Or 90%, right?
90%.
Factor of 10, right? So if I counted to this first number, which you could actually figure out, you'd have to start when the dinosaurs were alive and you'd be probably finishing around now. If you managed to count to that number, you'd only be 1/10 of the way to the second number. 90% of the work is still there, right? They look the same, but it's a factor of 10, right? If that represented the distance to California, the first number is the distance to Pittsburgh, right? You haven't even crossed the first state yet. That's a factor of 10. So when we deal with big numbers like this, we use scientific notations. You'd call that 10 to the 15. You'd call that 10 to the 16. And you go 10 to the 15, 10 to the 16. That's like the same thing, right? 15, 16, it's like less than 10% difference. But no, it's a factor of 10. So it's very easy to fall into that trap. Big numbers confuse us, right? Our eyes glaze over. We're just not wired to deal with that. We're used to like fingers and toes, right? That's what we think about. And if you think hard, maybe you can think about hundreds and thousands and stuff like that. Millions, billions, trillions, that's all illions with different letters, right? And we just lose it. And people know this, right? Politicians, lawyers, salesmen, carnival barkers, timeshare people, nothing personal for anyone out there. People know this and they will use it against you. They use the fact that big numbers, right? The national debt, the federal budget, how many pounds of CO2 do we put into the atmosphere every year? What's the population of the world? Big numbers, and we just kind of glaze over. So people will take advantage of that. So we really have to have a good way of keeping track of that. The same thing goes for really small numbers as well. We don't see that as much, except maybe in the sense of risk, right? If I go outside, the chance of getting hit by lightning is 1 in a million or something like that. Or the chance of winning the lottery is 1 in 100 million. We don't deal very well with that. So again, they sell lottery tickets based on that because we don't really understand small probabilities, right? The high reward outweighs the small risk of winning or small probability of winning. But of course, if you actually calculate the expectation value, you realize that playing the lottery is a loser in the end. And going to a casino is a loser in the end, right? Because the employees have to get paid, someone pays the electric bill, right? The house rake is real. But again, it's the shiny lights, it's the big payout, the jackpot. We're just very bad at estimating risk. So one way that we can get around these big and small numbers are things like scale models, trying to bring things down to a human scale. So you've probably seen these, again, trying to bring this back to astronomy. Have you ever seen these scale models of the solar system? Right, so they start with like a beach ball at the center, right? That's the sun, great. Right, so I go for a walk a little distance, and over here, this little BB or something, and that's Mercury. And then I walk a little further, and there's a little marble, and that's Venus. Then a little bit further, there's a marble, and that's the Earth. Oh, look, it's pretty, blue and green. A little further, then there's a little red one, and that's Mars. Then Jupiter is like, oh yeah, I see Jupiter over there. It's like a little baseball size thing. It starts to get a lot further. On that scale, you want to go to Pluto, you probably want to get in your car, right? Because that's how far away it is. It's either a long walk or a short drive. You make it to Pluto. Now, where's Alpha Centauri? 7,000 times further away. I hope you got gas money. So you get to Alpha Centauri. How far is Deneb?
1,500 light years.
So a couple hundred times further than that, you probably want to head to the airport. You made it to Deneb now after flying a few hours in a plane. Now I want to go to M13. I want to go to the Andromeda Galaxy. Yeah, call SpaceX. Scaling. Things get really big, things get really small, and maybe that's something that we have an advantage as astronomers, because these sorts of numbers, when they get reported on the news, they call them astronomical. We're used to this. We're used to dealing with big stars, things that are far away, galaxies that are 1 million light years away, and a light year is 6 trillion miles. We can think about these sorts of things. It still doesn't really compute. It just doesn't really gel in our brains, but we have some ways of sort of dealing with it, and that can really be helpful. All right, here's a couple of questions to think about. I don't have answers to all of these. I sort of jotted some of them down, but I actually left the paper at home. So how many musical notes are played by a radio station on a year? How many presidents, past, current, and future, are alive right now? How many carbon atoms are there in the human body? If you stacked up every hamburger sold by McDonald's in 2017, how high would the stack be? Anyone have any preferences? We'll look at. I have a lot more questions than I can cover. Presidents. Okay. So I can tell you right now how many presidents are alive. We got Carter, Clinton, Obama, Bush Jr., Biden, and Trump. So 6 are alive right now. One Bush. That would be 6, but I noticed I said future. We don't know who the future presidents are, and that's what makes this a Fermi question and not a Google question. Right? Current and former, we know that there's 6, right? We got 5 former, 1 current. How many future presidents are alive right now? probably some of them are kids in school right now, maybe some person in their 20s or 30s, maybe some staffer in a state legislature someplace. How could we estimate that?
Well, the average president is president for slightly less than 8 years. And presidents typically take office at an age, then I think the minimum age is 30 and the maximum age seems to be about 8. But let's split the difference and call it 50. So I need a 50-year supply of presidents at 8 years each. So I need 6 or 7.
So we'll add that to the current and past. So we had 6 plus 6 or 7 is about 13. Yeah. Another way we could go at it is, you could be president 4 years or 8 years, right? Those are kind of the two most popular choices, for people other than Nixon and a few others. Either 4 years or 8 years to split the difference, let's say 6. Average human lifespan, 80 years, give or take. There's one president at any given time. So take 80 years divided by 6, 13. Wow, about the same.
You're also assuming we still can keep our democracy.
That too, all right. All right, that's a very big assumption, all right, so we are making that. So obviously, right now, we don't know what the answer is, and we probably won't know for at least another 60 or 70 years. I did look up historically, and I think the high water mark for the maximum number of living presidents at one time was something like 16. And it was like in the mid 1800s, because remember there was a time there where there's like a whole bunch of one-termers, one after another. So you were pushing that 4-year rather than the 8-year limit at that point. So there was a time when there were something like 15 or 16. And again, they were mostly future. About 2/3 of them were people who hadn't been president yet. So it was like maybe in the maybe 1870s or 1880s, something like that. You had just some former presidents who were still around. And then you had like a bunch of like the first half of the 20th century were pretty much all, in school at that time. So kind of an interesting one. So a related problem, this is not really Fermi questions, but I think this is something that's interesting. Scaling. So how do quantities scale in relation to each other? Maybe I'll explain what this means. If I can drive 60 miles in 1 hour, how far can I drive in 3 hours?
180.
180. That's what we call linear scaling. Right? The longer I drive, the further I go. Right? If 3 men can dig a ditch in 2 hours, how many ditches can they dig in 8 hours? Right? Linear scaling is pretty easy. Quadratic scaling is where it goes is the square. So great example is, let's say they were going to do a project here. They have to spend our tax money. Let's say they wanted to take this room and they wanted to put tiles on the floor. Tile is 12 inches by 12 inches. So 1 foot square. How many tiles would it take to cover the floor in this room? Without doing any calculation, I can guarantee that every one of us, myself included, would be way off and almost certainly way too low. We are very bad at dealing with scaling like that. Unless anyone here does flooring for a living, then you might just know from experience. You come in here, yeah, we're going to need 5,000 tiles or whatever it is. Now, to do this, you'd have to actually measure the room, figure out how many square feet it is, and then figure out how many tiles you'd need. And the number is a lot bigger than most of you would think. Right? You just walk in the room, you probably figure, oh, like 1,000 tiles, right? 1,000 might get you part of the room right there, and then back to Home Depot for the rest. That's called quadratic scaling. Cubic scaling is things like volume and mass, right? Because that's length times width times height. We're even worse at that. Exponential scaling is another one. Right, this is the old story about the teenage kid who offers to cut his neighbor's lawn for 1 cent. It says, I'll do it every week after that for twice what I paid the week before. So first week is 1 cent. Second week is 2 cents. Third week is 4 cents. Fourth week is 8 cents. And this is great. The guy has only paid out like less than a quarter and had his lawn mowed for a month. But within a couple of months, the teenager owns the house. And we are really bad. Remember the early days of COVID, we were like, oh, we had 50 cases last week and 100 cases this week. How many next week? Well, 200, 400, 800, 1,600, unless we do something about it. So again, we're pretty good with linear scaling. We suck at everything else. So again, the lawyers, the politicians, the salesmen, they know this and they will take advantage of you. This is why the old thing at the carnival, remember the guess the number of jelly beans in the jar? People can't do it. And they'll put the dollar in there, guessing their number, and it's way off. Bacterial growth, right? That's a great example of exponential. Some examples in physics. Let's say a bird flying. So the lift, right, as the bird flaps its wings, the lift is roughly proportional to the area of the wings. Not exactly as a few other things, but roughly the area. But the weight, right, how much gravity pulls down, that's proportional to the volume, which goes as the dimension cubed. Right, so if I took the bird and just kind of expanded it to a bigger size, let's say I doubled its dimension, the lift would go up by a factor of 4, the weight goes up by a factor of 8. So as the bird gets bigger, the lift to weight ratio gets smaller. So I have some little examples here. A little hummingbird has its little wings and it flaps and it's perfectly happy to fly around. Bigger bird, like an eagle, has to have big, big, big wings in order to stay aloft. Then even bigger things like albatrosses, they got the big giant wings. And then of course you get a little bigger still and they just can't fly at all. But the wings, they would need to be so enormous that it's just not practical. That, then it becomes an interesting question of biology, which is that, these ostriches or emus, I'm not sure which one that is, they exist in some sort of a niche where the increased size has a greater survival advantage than the inability to fly pulls against them. Some other ones. There's a little mouse. What you notice about the mouse is it has these little wiry legs and it kind of sits there like this. And mice, they can turn on a corner. If you've ever had one in your house, those little things, they'll just run out and they'll just turn around in a second. Right? They can stop on a dime. They can, travel their own distance in almost no time at all. Here's an elephant. You notice the elephant has the big, thick tree trunk legs, and they're almost always in that straight out, maximally stable configuration. They can bend their legs, but really when they're standing, they like to be like that. So why is that? Well, their weight goes as the dimension cubed, but the strength of the limb goes as the dimension squared, because it's the cross-sectional area. So as an animal becomes bigger and bigger, again, the structural stability to weight ratio goes down. So if I just took a mouse and expanded it to the size of an elephant, it would just collapse. The legs would just collapse from under it. It wouldn't be able to support its weight on the little legs like that. Even though it looks exactly the same, because it's bigger, it doesn't scale. If I were on a planet, let's bring some astronomy in here. If there were a planet with a higher value of G, a higher gravitational acceleration, what do you think mice would look like? More like elephants. They'd have the tree trunk legs and they would kind of lumber. Now, of course, this comes as a disadvantage, right? Elephants don't move as fast, right? Once an elephant gets moving, it's not going to stop very quickly. But of course, elephants don't need to stop. They just run through whatever they come into. So again, it's a biology question of what's better, being kind of smaller and more adaptable, or being larger and not really having to worry about predators in the first place. Again, if we were on other planets, if humans lived on Mars, gravity is about 1/3. There are actually changes that'll take place in the body. You'll start losing bone density. You'll start losing muscle mass because you don't need to support yourself against as much gravity, which means you get back to the Earth and you're like that. If you were on a planet with higher value of G, we'd have a heck of a time getting around. You'd be trying to drag yourself around. Again, you'd expect to see lots of elephant-looking animals. Plants would be short because it's very difficult for them to get water up to a height. So you'd expect to see plants that are shorter. Another little example is a giraffe. Giraffes have their big long necks so they can reach up high into the trees. In order for that giraffe to get blood into its brain, it has to have very high blood pressure at the heart. So I read that giraffes have a blood pressure of like 300/180 or something like that. Let's say if you went into the doctor and they took your BP at 300/180, you're in an ambulance. All right, that's bad news. So giraffes have all sorts of adaptations. They have a much bigger heart. They have much thicker walled arteries in order to withstand that pressure. Because if they didn't have that pressure, then they wouldn't get any blood up to the brain. So again, lots of things that involve scaling. Now, of course, if I brought a giraffe to a planet with a higher value of G, it would just pass out because it wouldn't be able to get blood up to the brain. All right, here's a few more. How much square footage is needed for a 1,000-seat auditorium? So I'd approach a problem like that. Well, how many square feet do I need for an individual seat? Now, it depends. We could go, the Spirit Airlines route and we can stick everyone in as tight as possible. Or we could go the COVID route and we spread everyone out as far as possible. So you have to decide how many square feet each person needs and then multiply that by 1,000. How much would it cost to cover a car with postage stamps? I quickly did it. It's about $10,000. It's a lot. And you take your stamp, you figure out what's the surface area of a car. The surface area of a car is not that easy. So pretend that it's a box, where you could figure out length times width times height, figure out the size of each of those, and then start covering them with stamps. How many playing cards are equal to the weight of a school bus? So I guess the two questions there is how much does a card weigh and how much does a bus weigh? So a bus, I don't know, 20,000, 30,000 pounds, about 5 or 10 cars worth. How about a playing card? Probably. I mean, I'm thinking like a deck of cards. So about 50 cards is a few ounces, maybe. I'm in English units here and you're in metrics. All right. Yeah. So 50 cards might be quarter pound or something like that. So probably about a gram is probably where you are. So yeah, you divide the two by each other and you can figure out how many. Turns out the paper is pretty heavy. Another fun problem I did once, if you have a big roll of like toilet paper, like imagine big giant roll of toilet paper in the back of a truck, how much does it weigh? A lot. It's pretty heavy to the point that you actually have to be worried like it might actually like collapse. So when you're transporting things like that, you don't actually fill the truck all the way up because it couldn't support the weight. You'd only put a small amount at the bottom. How many photons are emitted per second by a light bulb? That's actually one that requires a little bit more physics. So that's part of the question. Yeah. Well, so let's identify what the important factors are. What's the power of the light bulb? So typical LED might be 9 watts, something like that. How much energy is in a photon? That's where we really get into physics. So visible light. Yeah, it's about 1 electron volt is about what you get. This is getting a little into electronics, but that's ultimately what you're doing is you're figuring out how much energy is emitted per second, divide by the energy per photon, and you get the number. And it's a big number. I'll leave it at that. So uncertainty and estimates. So nothing is known with absolute precision. You know, some things are only approximately known. So I have a little graph here showing some error bars. So sometimes a good technique is you might come up with an upper bound, like what's the biggest value something could have, a lower bound, what's the lowest value that I think it could have, and then a best guess, which is somewhere in between. If you don't really have a good idea of how to get the best guess, a useful concept is something called the geometric mean. So normally we think of, when you think of the average, that's called the arithmetic mean, right? You add two numbers, divide by 2, right? The average is 70 and 90, you add them, divide by 2, and you get 80. But if you have numbers that are varying over many orders of magnitude, this is actually a more useful thing. What you do is you take the upper and lower, you multiply them by each other, and then take the square root. So some interesting stuff. The mean of 1 and 100 is actually 10. So if something might be 1, it might be 100. 10 is actually in the middle of that range on what you might call a log scale. Or the mean of 1 and 10 is about 3. That's about halfway between 1 and 10. So when you're dealing with numbers that vary over these sort of large magnitudes, the geometric mean can be very useful. All right, a couple more, and I'm actually coming close to the end here. What is the power output of a microwave that boils a cup of water in 1 minute? This is where you wish you paid attention in chemistry. All right.
1 watt.
1 watt would take a long time. Probably at 1,000. That actually is about the answer to that. So how did you guess that?
No, what,
Just by knowing the microwave, yeah. And that is about it. You put a cup of water in there, about a minute. It'll maybe not quite boiling, but close. So the way to do it, so let's see. We want to know how much heat you have to put in. So
Got like the amount of heat to raise the temperature or something.
yeah, so that's that Q equals MC delta T or from chemistry. So we need to know the mass. We need to know the specific heat of water, right? This is where metric units help because it's 1 calorie per gram per degree Celsius. So if we get it right there, 1 calorie per gram per degree Celsius. So we want to know how many grams there are. How many grams of water in a cup?
About 150.
Let's see. So,
How many milliliters of the cup? Because it's 1 gram per milliliter.
so the way that I thought about it is I said a pint's a pound the world around. A cup is half a pint. So that's going to be half a pound, and half a pound is about a quarter of a kilogram. Quarter of a kilogram is about 250 milliliters. So 250 ml is about right. So a quarter of a liter or 250 grams.
Make an assumption on temperature.
For water, not really. I mean, for the volume or the mass.
Well, it's gonna take longer to pour energy to boil.
Oh, you mean for the temperature difference?
Yeah.
I thought you were talking about the mass and volume, because water has almost no change in volume as a
Yeah,
function
I
of
know, I know.
temperature. That's like a 1 part in 1,000 that we
Take it
would,
right out of the fridge or just take it.
yeah. So we have to figure out where we're going to go from there. So in Celsius, let's say you start at like 20 Celsius, that's like room temperature. And to boil, you want to go to, or in Celsius, 100. Right? So 80 would be the delta T. So MC delta T. You multiply those out. You have to convert calories to joules. So calories about 4 joules, give or take. So there's a 4 that goes in there. This is all the physics stuff that comes in. And then the power is just energy per time. And you get about 1,000 if you do the calculation there. All right, here's a fun one. What volume of snow lands in Pennsylvania over the course of a year? So how would we approach this? And then the second part is if we made it all into a giant snowball, how big would it be? So if we want to know the volume of snow, how would we calculate that?
Period times depth.
Area times depth. So imagine blanketing the state. Let's see, so Pennsylvania is kind of a rectangle. How wide is it?
350.
300 or so. Yeah, that's what's the end of the turnpike. It's like, is it 360 or something like that? 300 miles, 500 kilometers. North south, 100 and something. I know it's like a good 2 hours to drive. So yeah, it's about that. So you got about 500 kilometers by maybe 200, maybe 300 kilometers. What's the average depth of snowfall?
This year or 10 years ago?
Yeah, and also depends where. Are we talking here or are we talking Erie?
Pittsburgh's a lot more.
I feel like it's 19 inches a year.
19 inches. And yeah, the western part of the state is at least 2 or 3 times that. You know, Cherry Springs is probably 6 feet or something like that. So I think the average comes out to like 30 something inches, about 1 meter, which is convenient. So you figure out the length, you figure out the width, 1 meter in height. You can figure out the volume. You could figure out the weight from that. You'd have to know the density of snow. It's about 1/10 of liquid water. If we made it all into a giant snowball, what would be the diameter?
Volume. That's 4/3 by our.
You're making a good like New York snowball with like the ice in there. Good like South Philly snowball with the big ice chunk in there. You hit somebody, oh!
Volume is 4/3.
So 4/3 pi r cubed. So 4/3 pi is basically 1 as far as we're concerned. So it's basically r cubed. Well, for factors of 10.
Oh,
Yeah, 4, something like that. Yeah. Yeah. Yeah, it's about 4, but I think on the scale of this, it doesn't really matter very much. So 4/3 pi basically becomes 4 times r cubed. I did the calculation. It's about 3 kilometers is what you get out of it. That's actually a pretty good sized snowball.
15 pounds.
Yeah. So if we took all of Jeff Bezos's money in pennies, how big of a room would you need to store it? I want it to be the richest person. I think it's still Bezos. I don't know if Musk has taken over yet.
I think it is.
It is. Okay. So how much does Bezos have?
Trillion, something
Is he a trillion? I thought he was still like in the hundreds of billions.
He's in the
Let's say
500
500.
trillion.
500 billion. So if we made that into pennies, that would be 50 trillion pennies. So that's 5 times 10 to the 13 pennies. And then we have to figure out how big of a room would we need. Would it fit in this room? No, I think you need about 10 of these, maybe a little more than that. So you could figure out, the area of a penny,
So we fill this room with dimes.
dimes might actually do it. So you could- yeah, quarters, I think would. Yeah. Here's a fun one. When you take in a breath, how many of those atoms were breathed by Abraham Lincoln while he was delivering the Gettysburg Address? This is actually one that's gone around that people have estimated this, and you kind of come up with an answer, and it's larger than 1. So how would we approach that?
We start with the length of the Gettysburg Address.
Which is surprisingly short. It was like 2 minutes. So you could actually sit there and read the Gettysburg Address and then count the number of times that you breathe, maybe 100 times, something like that. Speaking for 2 or 3 minutes. Because you're talking, you're going to breathe a little bit faster. What's the average volume per breath?
2 liters.
I mean, 2 liters, like if you really blow out the lungs.
1 liter.
1 liter, maybe half a liter, something like that, for sort of shallow, normal
Every
breathing.
10 seconds.
Probably a little more than that when you're talking. Probably if you're asleep, it might be about 12 a minute. Talking would be a few times higher.
He's probably yelling.
That too, yeah. You can't hear him. Yeah. So he's yelling for 2 minutes, so probably a lot of breathing. Because there were no microphones back then.
Yeah.
So you're yelling for about 2 or 3 minutes. Calculate how much air they breathed out. Then the assumption is that it drifts out and it becomes sort of equalized through the atmosphere. Now, if I breathe in maybe that half a liter or 1 liter. You can figure out what fraction of that is Abraham Lincoln air, right? Because it's just whatever fraction that is of the total atmosphere. So you got to estimate the total volume of the atmosphere.
Avogadro's number.
Avogadro's number definitely comes in there because you're going to figure out how many molecules, right? So if I breathe in half a liter, so 1 mole of gas at STP. You remember their chemistry?
6.23 times 10 to the 23rd.
Yeah, 22.4 liters is 1 mole. So if you breathe, say, half a liter, that's 1/40th of a mole, or sorry, 1/4 of a mole. No, 1/40th of a mole. So 1/40th of 6.02 times 10 to the 23. You can figure that out. That's the number of molecules. Then multiply by that, the fraction that's Abraham Lincoln air. And the answer you get is like 100. So it turns out it's actually more than you might think. So the volume of the atmosphere is actually kind of tough too, because the atmosphere's density changes, right? Because the atmosphere goes up like 100 miles or so, but most of the atmosphere is within 5. Yeah, it's exponential. It goes forever. But yeah,
You're asking the aeronautic engineer.
yeah. Although the vast majority of the air is within like 5 miles of the surface. There's a couple of ways. The way I did it was I said air pressure at the surface is 14.7 pounds per square inch. So that means if I have a square inch over here, there's 14.7 pounds of air sitting on top of it. And then I said, well, how many square inches is the Earth? So figure out surface area of the Earth, 14.7 pounds of air on each. You figure out how many pounds of air there is around the Earth, Avogadro that, and you can figure that out. Yeah, you get a number that's on the order of 100, maybe it's like 50, maybe it's 200, something like that.
For every breath.
For every breath you take.
But that's every person that's ever lived. It's Christ, Da Vinci, everybody.
Yeah, so you're breathing Christ's air and George Washington's air and Abraham Lincoln's air and Hitler's air. Yeah. You're also drinking dinosaur pee. That's another one you could figure out how many, when you drink a glass of water, how many molecules of Brontosaurus pee is in there. Kind of an interesting thing. Yeah, so you can have a lot of fun with these sorts of questions. So I hopefully presented it in kind of a fun way, but hopefully you have some ideas to think about, especially about large and small numbers, the scaling ideas. So why does nature look different on different scales? I mean, here's another nice example. Suppose I find a roach. I go, I don't want roaches in here, but I'm feeling really nice. So I take the roach on a little piece of paper over to the window and I flick it out the window. Roach kind of floats, lands on the ground and walks away and does his roach stuff. But if I did that with something larger, and I have to be very careful here, I don't want to get accused of, inhumanity to animals or anything like that. If I did that to a larger animal, it would splat on the ground. Why is it different? Why does the roach get away? Surface area to volume, right? Because the roach is very small. So as it's falling, there's a lot of drag, right? Because its surface area is large compared to its volume. There's a lot of drag, so it reaches terminal velocity pretty quickly and then just kind of floats down at a normal speed, kind of hits the ground and goes, all right, That's it.
Surface area, mass, not.
Surface area to mass, yeah. But volume basically scales with that. But you're right, there is a point about volume and mass, because like birds, for example, have hollow bones, so they have lower density. That's one of the ways that they're able to fly. So it's an interesting calculation. You know, if a human being wanted to fly, you could try to calculate how big the wings are, and it's just enormous. And we wouldn't be able to. We just wouldn't have the strength to be able to flap wings like that. It would have to be really big. Now, maybe if we had hollow bones and all that other stuff, even then it would be very, very tough, right? Because, you know, 150-pound human, that's, you know, bigger than like an emu or an ostrich. So I don't think we'd ever be able to fly. But it also means you can't scale things up, right? You know, they have all like these science fiction movies about like people who get like scaled up to like 50 feet or 100 feet. I can tell you, first thing that would happen is their legs would collapse from under them, right? It wouldn't end very well, right? Here comes the giant, and then just fall over. Because A, the legs would collapse. B, there wouldn't be enough blood pressure to supply any blood to the brain, so they wouldn't be able to be upright.
So you're saying we shouldn't learn science from?
Yeah. Yeah. Yeah, so that would happen, you know, unless we had some major physiological adaptations that we could be larger. I mean, and we know this from experience, because, you know, larger humans, people like Andre the Giant, Robert Wadlow, who's like 8 feet tall, didn't live very long because they had a lot of health problems, because the human body is just not made to be that big. So that happens. Yeah.
If the Earth was the size of a proton, how big is the universe?
So let's see. So we go from 10 to the 7 meters down to 10 to the minus 15. So we shrink it by 10 to the 22. All right, so the universe, call it 10 billion light years, which is.
I know, I think it's hard. It's hard. I think it's 60 billion.
It
It's
depends.
this way and this way.
Yeah, it
and
depends.
this way
Yeah, it
and
depends
this
on how
way.
you define it, because the furthest galaxies we can see are 12 billion light years or so. But that's because the light has been traveling towards us since the Big Bang. Those galaxies are actually much further away now.
Exactly.
So yes, 10 billion, something like that, light years. That's 10 to the 10 light years, and a light year is 10 to the 11 kilometers, so 10 to the 22. So yeah, the universe would be about a mile or a kilometer in diameter if the Earth were the size of a proton, if my math in my head is correct.
Take all the people on Earth, where could they fit in? What city or state? 8 billion.
So it depends how densely do,
No,
are we talking like standing room only?
In the chair.
Put them in a blender. Yeah, we're definitely going to get reported on YouTube now. Take everyone, put them in a blender. Yeah. I guess there's also questions, can you have everyone living like that? Because, you know, you need farmland, you need drainage space.
hypothetically, if you just put them together, how many there?
I think it turns out to not be that large. I think you could fit everyone in kind of a large city or like a state size. Yeah.
The high rises?
Yeah, so Hong Kong has a couple million people in a fairly small area. So multiply that by 1,000. And 1,000 means 30 times bigger that way, 30 times bigger that way. So imagine 30 Hong Kongs by 30 Hong Kongs. That's not that
They
big.
also go.
Oh. Yeah, Manhattan is 2 million people in, you know, sort of a sliver. So
Yeah, but
imagine,
you said you wanted to. No,
Yeah.
compensate for the flat surface. Houston or something?
so 1-story buildings. Yeah. But yeah, then you get into problems like with infrastructure. How would you supply the electricity? How would you supply the food? How would you have roads?
Where's the pool? Same with-
Where's the pool?
There
I
are
want
more,
somebody to go to that.
there are more stars in the universe than there are grains of sand. Is that correct?
I believe so. We could probably try to figure that out, right? We have a beach, and how big is a grain of sand? 1 cubic millimeter or something like that. So how deep does the sand go in a beach?
Will the Webb telescope help us with that?
Just counting the number of
Determining
stars.
Stars or galaxies in the universe?
And I guess that's the number of galaxies probably kind of known already, because, you know, we have samples like from the Hubble, right? From the Hubble Deep Field. We know about how many galaxies there are. This is another Fermi type question, right? You look at a little area and there's like 1,000 galaxies. How many are there in the entire sky? You multiply by that.
What, you know, we're going to talk about, what range is it look over? IR visible?
It's almost all in the IR. It's from like, it was about 400, oh no, 600 nanometers, so like in the orange down to like 30 microns or something like that. Yeah. Yeah, so that was a deliberate choice. Yeah, it's unfortunate that they won't have the short visible and the UV. That's something that, especially the UV, Hubble was really unique at that because it's not something you can do from the ground. So I don't know what the plan is. If Hubble gets retired, we'll have basically no UV instruments other than maybe some aircraft-based things. So that is a limit. But yeah, with Webb, it was chosen to go to infrared because the stuff they're looking at is mostly very strongly redshifted by factors in. Yeah, that makes it a lot cooler. So you could see further into the infrared.
I
Yeah,
have a math question.
yeah.
How long will human civilization last?
Ooh. Yeah. I mean, this is the big debate when people talk about the Drake equation. And actually, the Drake equation is a great Fermi question. So the Drake equation, if you've seen it, starts off with astronomy things like how many stars are there in the universe and what fraction of planets are habitable. You know, those were things that we kind of had to wave our hands, you know, a few decades ago. But now we actually have some data to drive that. How many stars are there? How many planets are there? Things like that. Then it gets to the hard stuff. I mean, fraction of planets that develop life, I think is probably pretty high. The chemistry is pretty robust. So if you have the right chemistry, you'll probably get life. But how many of those will get to intelligent life, right? How many of those will get to like the level of humans? And, you know, how many of those human civilizations will last long enough to get into space and stay there? Actually, since we're on the topic of Fermi, there is something called the Fermi paradox. And this actually came out of questions like this, where, you know, they took, you know, these sorts of calculations like we did with the civilizations in the galaxy. And basically, you know, if you look at those, the astronomy numbers in the beginning of the Drake equation, they're all big. They're all millions and billions. They're high numbers. And that turns out that there should be millions or billions of civilizations in the universe. And the question is, why aren't we hearing from any of them?
We haven't seen any of them.
We haven't seen any yet. We haven't detected anything anywhere. I mean, not that we've looked all that hard, but if they were out there, why haven't we seen them? I mean, I'm discounting like alien abduction stories and things like that. Why haven't we seen them?
Or they seen us.
Or have they seen us? I mean, there's a few answers to it. You know, one is that they're out there, but we can't see them, right? They're communicating some other way that they're using neutrinos or something that we can't detect. Or maybe they're deliberately hiding from us.
Or they're too far away.
That maybe they have, you know, their United Federation of Planets and their rule is that we don't communicate with primitive civilizations, and we're primitive on that scale.
Even we're too early or we're too late.
Yeah, time would be another possibility. And I think that's probably the answer, is that everything is just spread out in time. Is that there were other civilizations, you know, millions of years ago, and there will be many more. And it's kind of sad. It's like a bunch of flashes in a pan. Yeah. Or the other idea that's come up is the idea of a bottleneck, is that you have all these big numbers, and then one of the numbers in there is just really, really small. You put something in there that's 10 to the minus 12. So maybe the probability that intelligent life emerges is really, really small. And in that case, we can kind of pat ourselves on the back because we made it over the bottleneck. Or maybe the bottleneck is in the future, right? Maybe it's the very things that enable us to communicate over long distances are the things that will kill us. Maybe it's the nuclear weapons and rampant industrialization and not dealing well with viruses and God knows what else.
Carbon dioxide.
Carbon dioxide. Maybe the bottleneck is in our future, and maybe we're about to discover what it is. We're about to discover why there are no advanced civilizations out there, because we're going to go the same way they did. But maybe if we realize that in advance, maybe we can come up with a way around it. I don't know. A couple of years ago, maybe I would have felt more optimistic, but I don't know.
Let's do like, how many cupcakes can you fit?
All right, there we go. Optimistic. All right. Yeah, Henry.
Trick question.
Uh-oh.
What is the average number of people killed by meteor strikes every year?
Average number of people killed by meteor strikes.
On this planet?
Yes, human beings on this planet.
would be pretty close to zero.
Well, you start with the 1 in 100 million chance of wiping out all 7,000 million of us at one blow, and suddenly the number is over 70. I
Yeah.
told you it was a trick question.
Yeah. And it's one of the examples of human beings being very terrible at dealing with these sort of low risk, high reward situations. Right? You know, the chances that we'll have a meteor strike in the next 10 years are very low. But if it happens, it's millions of people dead, maybe billions of people dead. So yeah, if you average that out over, say, 1,000 years, it could end up being one of the larger threats to human life. And maybe not up there with malaria or warfare or something like that, but
After dinosaurs.
certainly. Yeah. So if in the next 1,000 years, 1 million people die from an asteroid strike, that's 1,000 people a year that died. Not huge on enough sort of public health. That's 1 milli-COVID, I guess. Because COVID is now 1 million people died from that. So 1 milli-COVID.
When you use those numbers, you gotta take out, people would have died anyway.
Yeah.
So it always looks bad.
So that might lower the number a little bit.
People die.
Not 1 million.
The point is that nobody does that analysis. So we don't know.
Well, I mean, the number of flu deaths is pretty well known. It's between 10 and 50,000 a year, typically.
Has anybody done a rigorous study of what the Delta mortality was?
Of just the Delta variant alone.
No,
Oh, the excess deaths. Yeah, the CDC has that. They have the number of excess deaths compared to what would be expected. And it's, I remember in 2020, it was like 300,000 above what would be expected. So the normal is like 2.8 to 2.9 million. And that year was like 3.1 million. Yeah. Well, the excess deaths is everybody, right? Everybody who dies, they count those. And then you just have a larger number of basically deaths in a year of all causes. And if you see that difference, that's probably COVID for the most part. Might not be that they died of COVID, but they were extra people that died as a result of the pandemic.
the number that gets reported is COVID.
Yeah. Yeah. And the excess deaths were, I think, 30% higher than that. So the COVID reported deaths were actually an undercount.
West Nile virus has been found in Philadelphia. I guess there's-
More good news.
Very
Monkeypox, do we have that yet?
Not yet.
Oh, we do 2 monkeypox. All right. Remember, if there was 1 last week and 2 this week, then is it linear or is it exponential scaling? Yeah. Of course, next week might be 3 or 4 because it's statistical uncertainty. So we don't know which way it goes. Yeah, unfortunately, a lot of this stuff, by the time you get the answer, it's already too late.
I will tell you that the American Meteorological Society, notwithstanding the danger of meteors, doesn't believe in meteor control.
Shouldn't they study meteors? Because they're meteorologists. Right. Are there any other questions? Anything on YouTube? All right. This has been fun. Hopefully thought-provoking. Yeah, Bill. Okay. Lou, does Lou want to talk to me? Which Lou? Greek Lou or other Lou? What does he want to say? All right. All right, let's shut that down.
What was that answer to Abraham Lincoln breath question? 100?
I think it's on the order of 100. I did it a couple different ways.
Per breath.
Yeah, or molecules. I guess the one big uncertainty there is we're assuming that it's the same air the whole time.
Yeah.
Because some air does get sunk. It goes into the oceans, it gets mineralized, and then it may not come back. So if that's the case, the air that's here now might not have been air 100 years ago. Right? It might have been in the ground. Right? It could have been in seawater, things like that. So that is a big assumption that you don't have much transferal in and out of the atmosphere.
to say something. Is that what I heard?
Yeah, he just wants to go on Zoom.
Pardon? Lou wants to come on. Okay.
Oh, but we're on a different Zoom.
Yeah.
I wasn't able to get in.
When you stop the.
He won't be able to get in. It's a different link. Well, if he has something, you could just read it out.
No, he doesn't have anything, he just wants to chat.
Oh, all right. Sorry.
All right. We're back here in July and we're at Fort Washington in August. Thanks for coming.
All right. Thanks for joining us. We'll see you next month.